Hi, the lecture today is about implicit differentiation. Hi, today we are going to talk about implicit differentiation. So the item one that we are going to talk about is if I have a function that is given to me in an implicit way, which means some relationship between x and y is given, but y is not necessarily given in terms of x explicitly. How do we find derivative of y with respect to x? I will talk about that shortly. Next, we are going to apply this to finding derivatives of inverse functions. Inverse trig functions. These are things that you might be calling arcsin. Some other books might refer to it as asin. Some other books might refer to it as sine inverse. And similar notation used for all the 6 trig functions. We are going to talk about that. And last, if we have time, we are going to talk about finding properties of orthogonal families of functions. Orthogonal is a fancy way of referring to items that are perpendicular to each other. We are going to talk about curves that are perpendicular to each other. Let's go take each of these items at a time and see how we are going to handle them. Item number one is implicit differentiation itself. First of all, what do we mean by implicit? Most of the functions that you see in Calculus 1 are explicit functions. Explicit functions simply means that you have a formula to apply and find the value of dependent variable in terms of the independent variable. Here's an example. Suppose if I tell you y is equal to x squared plus x. What does this mean? Well, x is your input, y is your output. Output appears alone by itself on the left hand side, and here on the right hand side you have a recipe of things to do to x, to your input, to get the output. So once you perform these steps, you are clear about what the value of y is going to be. These are referred to as explicit functions. Here's an example of implicit function. Suppose I tell you x squared plus y squared is equal to 4, and perhaps I tell you say y is a positive quantity. Well, here if I tell you the value of x, you still need to go through some steps rather different from here to find the y. Sometimes that is easy, sometimes that is hard, sometimes perhaps impossible in a certain sense. For example, here you would have said y squared is equal to 4 minus x squared. Then you go ahead and solve this thing, you say y is equal to either plus or minus square root of 4 minus x squared. And given that you were told that y is a positive quantity here, or at least non-negative quantity, your final answer would have been y is equal to square root of 4 minus x squared. So you go through a sequence of steps to find y in terms of x. So these steps, we refer to it as finding y in terms of x. As I mentioned, sometimes it's rather straightforward, sometimes it's hard, and sometimes it is impossible. Now, if I want to investigate the derivative of y with respect to x, the question is, what would I do? If I want to find the derivative of y with respect to x, if I could go ahead and easily find y implicitly if I could go ahead and explicitly find y in terms of x, well, I could of course go ahead and differentiate this one. For example, in this exercise you could say, well, this y, I can write it in a different style. I can write it as 4 minus x squared to power of 1/2. And if I want to differentiate it, I'm just going to apply the power and chain rule, take the exponent, and then say 4 minus x squared to power of, reduce the exponent by 1 notch, and then differentiate the base, and then clean this up. So, for example, we would say derivative of the base here is minus 2x. This factor of 2, I might put it here. And this is a factor of minus 1/2, which makes a radical in the denominator, 4 minus x squared. And then I could cancel the 2's, and then I'll be done. This is minus x over radical 4 minus x squared. So if we were dealing with an equation that was simple and could be solved, then differentiation itself would not pose much of a challenge. But question that you have in mind is, what if we are facing something like this? Suppose I have x cubed plus xy plus y cubed is equal to, say, 1. And the question is, find dy dx. Well, there are technical questions about is this defining y as a function of x or not? For a moment, we are going to put that aside. Suppose we don't have that complication, and our attempt is, well, what do I do to find this derivative? Our first thought could be, well, let's go ahead, try to find y in terms of x, just like what we did here, and then once we have it, we are going to differentiate that. In this equation, it is actually possible to find y in terms of x, but it's going to be quite complicated. It takes a couple of lectures before we get there. And then once we get there, the formula itself is going to be complicated, and differentiating it is not going to be as easy as this. So we start to think about some other ways of handling this as opposed to this direct approach, and that is the implicit approach. Implicit approach says it might not be worth or even possible to solve this equation, but there might be a possibility of finding the derivative even without it. Of course, we are going to pay a price, but it's going to be better than the alternative. What is the approach? The approach is to think about y. We know that ultimately y is going to be some function of x. So we keep in mind that y is a function of x. You don't see it, and that's a problem. You just don't see what function is it. So that function is an implicit function. It's an implicit function. We don't even try to find it. You just keep in mind that y is a function of x. So sometimes it might be beneficial if you tell yourself y is is something that depends on x. Instead of f of x, sometimes people write it y is equal to y of x to emphasize that y is actually a function of x. So what does all that mean? Suppose I want to differentiate y. What does that mean? Well, y prime is dy dx. And we want to differentiate y with respect to x, but we don't have a formula to differentiate. So that's where we stop, and there isn't anything else to say right now. Suppose I want to differentiate y squared. Or perhaps you want to write it in this notation, d dx of y squared. What would I do? Keep in mind, again, y is a function of x. So differentiating this would have been differentiating any kind of expression, any parentheses raised to power of 2. How would you have differentiated it? You would have taken the exponent up front, you would have reduced the exponent one notch, and here's a critical step not to forget. Then you have to differentiate the base as well. Let's emphasize by rewriting this in a notation that is a little bit less cluttered. y2 prime is 2y prime. Here we mean the derivative is being taken with respect to x. We are not saying it out loud, but that's what we have in mind. Let's try it again. Suppose you had y cubed and you want to differentiate that. Again, you're keeping in your mind that y is some nasty function of x. We don't know exactly what, but differentiating cube of that would require taking 3 in front and reducing the exponent to 2 and then multiplying by y prime and so on. So if you had any power of function y, you want to differentiate it, you just have to use the generalized power rule. So what is important in all of these things is the presence of y prime in all of them, and that is not to be forgotten. Now let's see how does this show up in our equation, in our problem. Our problem was here I have x cubed plus xy plus y cubed is equal to 1. Is that what it was? Let's see. Yes. Find dy dx. Our general rule of thumb would be, given any such problem, we just go ahead and differentiate both sides with respect to x as it is, just so that our answers will be comparable. So we're just going to go ahead, differentiate with respect to x. Everything that is in sight is going to be treated with this differentiation. Well, some of these are easy and some of them will take a little bit time to see. Derivative of 1 with respect to any variable, but that is of course 0. Derivative of x cubed with respect to x, well, that's a familiar function. You're differentiating x cubed with respect to x, and the answer is 3x squared. Let me pause on that one and go handle this. Y cubed. Differentiating y cubed. What you need to struggle with right now is that we are differentiating that thing with respect to some other variable. So the formula that's applicable, you have to keep in mind that has this influence of chain rule in it. Derivative of y cubed with respect to x is 3y squared y prime. You might be wondering why isn't that we have an x prime here? Well, x prime is derivative with respect to x of x. That's just 1. So if you want to insist on saying a derivative with respect to x of x cubed has to be 3x squared x prime, that's fine. It's just that x prime is derivative of x with respect to x, slope of the line y equal to x, that's just 1. So that's why this doesn't get to be written. But derivative of y cubed with respect to x, derivative of any variable with respect to some other variable, will have that prime in it. Now let's go to the other one. Derivative of xy. What is involved here? Well, we have a product. Derivative of the first times the second, to 1 times y. First times the derivative of the second. Derivative of y with respect to x is just y prime. So in this problem you see that we have plenty of y primes here. And what is it? Well, that's really what we want to find. So what we are going to do is try to solve this for y prime in terms of x and y. So I write y prime, the item I want to find, times, I factor whatever has y prime in it. So I have x plus 3y squared. Anything that doesn't have y prime in it, I just send it to the right hand side, minus 3x squared minus y. So these two items just came here. Now I want to find y prime, so here's my y prime. Y prime is equal to, just divide the right hand side, minus 3x squared minus y divided by x plus 3y squared. That is our answer. You are not used to these type of final answers, but let's review what happened. We started with x cubed plus xy plus y cubed equal to 1. The question was, what is y prime? What do you mean by y prime? I mean derivative of y with respect to x. We said you could go ahead and find y with respect to x and differentiate that, but that's going to take a week before you get there. Alternative way was to differentiate in an implicit fashion. We did that. We got an answer, and the answer has something peculiar about it, which is it is also implicit. Right hand side isn't just an x, but is a mix of x and y. So we didn't separate x and y from each other here, and the price we pay is that our answer is going to have the same flavor. It's going to be a mix of x and y's to it. So that's called the implicit derivative. Let's go ahead and do another example similar to this. Let's take something perhaps similar and then something a bit different. Suppose I have x squared y plus x cubed y to the power of 5 is equal to y plus x. Question is, find dy dx. If the variable names were different, you adjust accordingly, but here we follow the traditional format that x is the independent and y is the dependent one. So we have to go differentiate these things. Differentiate everything in sight. We might as well write some of the easy ones. Derivative of x with respect to x is just 1. Derivative of y with respect to x, it's better in my view to write it as y prime because it's a bit less cluttered than this one. But if that's what you're used to, just continue using that. Derivative of x squared y. I have to differentiate the first. It's going to give me 2x times the second plus first times the derivative of the second. So this is what came out of here. Plus, for this one, derivative of the first, 3x squared, that's the derivative of the first, times the second, plus, first is x cubed, derivative of the second, y to the power of 5, 5, y 4, and here's where you shouldn't go wrong. You need a y prime because you're differentiating with respect to something else. Keep in mind that you are trying to find this quantity, y prime. In all of these problems, this stage, everything becomes straightforward. You have to go ahead and factor that, y prime. Here you have an x squared. Here you have 5x cubed y 4. This one is on the right hand side. It should have been really brought to the left, but let's combine the steps. If it comes to the left, it's going to be minus y prime. Is that right? So I just wrote minus 1. Everything that doesn't have y prime goes to the right. I have 1, 2xy I had over here, 3x squared y5 I have over there. So here's our holy grail. So y prime is equal to the right hand side, 1 minus 2xy minus 3x squared y5, and here I have x squared plus 5x cubed y4 minus 1, if I'm not mistaken. So that is the general flavor of all of these problems. Some of them maybe have a mixture of all sorts of other functions thrown in. It's just that you have to be careful about the y prime portion. Let's take something here. Suppose I take, here's another example, 1 plus x plus y is equal to sine of x y cubed. You see, this is a really nasty looking equation. There would be no hope of separating x and y by any of the means we know in algebra or even trigonometry. So it obviously recommends itself for implicit differentiation. So again, we go ahead and differentiate. Our question is find dy dx, y prime. We want to find that. Okay, derivative of 1 is 0, derivative of x is 1, derivative of y is y prime. That was the easy part. Right hand side, I have to differentiate this. Now we have to apply chain rule carefully. Derivative of sine, that is cosine. Whatever that function was applying to, the derivative applies to that. By the chain rule, then I have to go ahead and differentiate the interior also. The interior function has to be differentiated. So I still have this prime. So I go ahead, 1 plus y prime is equal to cosine of xy cubed times, okay, how do you differentiate that? That's a product rule. Derivative of first times second, so y cubed. Second times first, 3x y2 y prime. Again, let's go ahead and color. Everything is colored, but color in a different color. And remember, we are trying to catch y prime. Here, I might as well go ahead and open everything up, bring everything to left hand side. Perhaps that's going to be easier to see. 1 plus y prime. I bring this cosine of xy cubed times another y cubed. I bring it to the, well, let me just open it on the right hand side as it is. Perhaps that would be cleaner. Cosine of xy cubed. And this one is 3x y2 y prime cosine of xy cubed. Just change the color of what we are trying to find so it's not buried under all the clutter. So I'm going to bring my y prime to this side. Y prime, I factor y prime, factor this one, bring it to the left, 3xy2 cosine of xy cubed. The right hand side is y cubed cosine of xy cubed minus 1. And here's final. Final round is always the same. You just divide the right hand side by coefficient of the left hand side. Okay, I hope you saw the process here. Some of the problems here, they ask you to find the slope of the tangent line at some point to an implicit curve. Well, you go ahead and figure out the slope from here. So you plug the x and y that you have here to get a number for your slope. So at that point, then you have a point and you have a slope, and you go ahead and write the equation of the line as usual. So I leave those problems to you. Next, we are going to go ahead and apply this in a simple setting to inverse trig functions. So we are going to talk about derivative of inverse I hope you have done the review of trig, particularly inverse trigs, so that these things that we are going to talk about wouldn't sound just like a bunch of formulas, but hopefully will have some content to them as well. Let's start with basic one, arcsin of x. Now, just for benefit of you who are used to different high school text, sometimes this is written as asin, so that the word doesn't look so long. Sometimes they use notation that is used for all the other inverse functions, putting a -1 on top of it. Okay, so we have different three different ways of talking about the same thing. Just quickly going over what this notation means. You all remember that sine of 30 degrees or sine of pi 6 radians. Do you remember what that one is? Sine of 30 degrees is 1/2. So here you are starting with the angle and you are finding sine of it. Sometimes you want to go in reverse. That is, you know the sine, you want to know what was the angle that had that sine value. So you might write it like this: sine inverse of 1/2 is equal to, say, 30 degrees, and or equal to pi 6 radians, and so on. So these two statements mean the same thing. But you really need much more review of arcsine and arccosine and all of those functions before we go on. So you go ahead, take a look at those items, come back. Okay, suppose I have y is equal to sine inverse of x. I'm using this notation now. According to this, what does that mean? Here we said sine of 30 degrees will be 1/2. Is that right? Sine of 30 degrees is going to be 1/2. Here also, this means sine of y is equal to x. If y is equal to sine inverse of x, then sine of y is equal to x. What do we want? We want dy dx, or we want y prime. This is a function that is new for us. We don't know how to handle that, but we know about the function sine. We have worked on that just last time. So I go ahead and differentiate this one, but there's a price attached to it. This equation is an implicit equation. I have to differentiate it just like those differentiation we did. So let's just first write what we are going to do. Sine of y, I'm going to differentiate with respect to x. Next, I'm going to say, well, derivative of x, that is easy. Derivative of sine is going to be cosine of whatever this was being applied to. And by chain rule, I have to differentiate the interior function as well. Y itself is some function. Its derivative is to be found. So we are trying to find that. Here's derivative of the interior function. So now y prime, which is item I wanted to find, like all those other problems we had done. Here's y prime I'm trying to find. What's y prime equal to? It's equal to 1 over cosine of y. So what is the derivative of sine inverse of x? We found that the answer is 1 over cosine of y. In our previous set of problems, this would have been an okay place to stop, but in all the examples we are going to look at now, we are going to go one step further, which is to find this in terms of x. That's the preferred way. If we could make the derivative to look in terms of x, we have made some progress. So we want to know what the derivative is in terms of x, going one step beyond what we have done for implicit differentiation. Well, how do we achieve that? So you know what sine is. So can you figure out what the cosine is? What's the connection between the sine and cosine? You are giving me that information and you're expecting me to find this one. Is there any connection between sine and cosine? Well, that is a basic trig identity. Let me write it on the side. What's the connection between sine of x and cosine of x? That very sine of sine of y and cosine of y. Between sine and cosine of any angle, there's a very famous formula that connects them, establishes a relationship, which is this Pythagorean identity. It just tells us that sine squared plus cosine squared is equal to 1. So if I wanted to figure out cosine, I could say cosine square of y is equal to 1 minus sine square of y. And if I want the cosine of y itself, now here's a problem. I have two choices, plus or minus 1 minus sine square of y. Now comes a technicality to help us choose which one of these two signs is going to be picked up. Remember, from the definition of inverse sine function, inverse sine gives you an angle that is either in the first or fourth quadrant. That's by convention. Inverse sine always gives you an angle in the first or fourth quadrant. So let me write it here. When we say y is equal to sine inverse of x, y is an angle in quadrant 1 or 4. Let me write it again. Not readable. So if by the definition of sine inverse, if the y is an angle in quadrant 1 or 4, what would the cosine of it be? Cosine of an angle that is in either of these quadrants is a positive quantity. At least is going to be 0. So that tells us from these two choices, the choice that is going to be picked is cosine of y is equal to radical 1 minus sine square of y. Now what was sine square of y? Now sine of y is x. So sine square of this will be x squared. I go back here and write this as. So after all of this work, what we have achieved here, the y prime, which was 1 over cosine of y, we figured out cosine can be written in terms of sine from this identity. We made a correct choice for this plus or minus, And also we replace sine of y with the x itself, and here's our final answer is a 1 over radical 1 minus x squared. So let's paraphrase everything. Sine inverse of x, if you differentiate that, you get 1 over radical 1 minus x squared. Sine inverse is defined for numbers from 1 to minus 1. At 1 on minus 1 itself, this right hand side becomes infinity, telling us that we are going to have a vertical tangent line. All of that can be understood if you do a quick graph of sine inverse. If you remember from the review of inverse Trig's graph of sine inverse, you might as well start with the graph of sine itself. Suppose this is the graph of sine. So this is y is equal to sine of x. Then you flip it across the 45-degree line. So let me draw the 45-degree line. This is y is equal to sine inverse of x. Sine inverse of x, its domain is from minus 1 to 1. At these last two endpoints, it has a vertical tangent line because sine x itself at this point reaches its horizontal tangent line. So we learn how to figure out the derivative of sine inverse. Now we have to do this thing 5 more times for cosine, for okay, there was an interruption there, so I'm coming back to this formula for arcsine or sine inverse, and we want to do another one for cosine. Just before I go there, let me just remind you that the same formula might be written like this: arcsine of x differentiated is going to give you 1 over radical 1 minus x squared, or if you write it this way, arcsine of x differentiated gives you 1 over radical 1 minus x squared. These are all the same, of course, it's just a different way of writing it. By the way, you do have a button for arcsine on your calculator. Make sure you locate that. Different calculators have different styles to it. Maybe you need to read the manual and see how that goes. Okay, next formula we have in mind is cosine inverse of x differentiated. This one turns out to be minus 1 over radical 1 minus x squared. So what we are going to do is to understand where does this come from as an example of implicit differentiation. You could also do this thing by just pure geometry. Let's go ahead and pick our function y is equal to cosine inverse of x. That's our starting point. If y is equal to cosine inverse of x, just like the case of sine, means x is equal to cosine of y. If you have that, same as saying this. Now I go ahead and differentiate this thing with respect to x. Differentiating, so I say differentiate with respect to x. Derivative of x is going to be 1. Derivative of cosine is going to be minus sine, and derivative of y is going to be y prime. So y prime becomes minus 1 over sine of y. All that is left to do is to describe the formula for the derivative in terms of x. It is given in terms of sine of y. I know cosine of y is x, just like last time. What's the connection between these two? We know that sine square of y plus cosine square of y is equal to 1. Therefore, sine square of y is equal to 1 minus cosine square of y, and therefore sine of y is either plus or minus 1 minus cosine square of y. Now cosine of y itself is x, so sine of y that I need in this formula is either plus or minus 1 minus x squared. Again, comes to the tricky issue of what choice should we make here, plus or minus. Just remember that when we say y is equal to cosine inverse of x, the angle y defined here is, by definition, is in first or second quadrant. Y is in quadrant 1 or 2. Cosine inverse of an angle is always defined to be an angle in the first or second quadrant. Therefore, the sine of y, say since y is in quadrant 1 or 2, we know that sine of y is going to be positive. So the sign that is going to be chosen from plus or minus, plus is the correct answer. So sine of y for us is going to be just radical 1 minus x squared. That finalizes our formula here. Y prime becomes minus 1. Instead of sine, I will write 1 minus x squared. That finishes it up. So let's repeat ourselves. What we discovered is that cosine inverse of x differentiated is equal to minus 1 over 1 minus x squared. Again, same kind of caution should be applied as x equal to plus or minus 1. That's where the graph of cosine inverse is going to have a vertical tangent line. Let's go and get ready for the next one of these formulas. The next one we have is the following formula: tangent of x, tangent inverse of x prime is equal to 1 over 1 plus x squared. So what we want to do is to go ahead and show where does this come from by using implicit differentiation. So let me see if I can encourage you to stop this thing and go ahead, make a proof yourself and come back. How about that? You start with this: y is equal to tangent inverse of x. You go through the differentiation, and then you have to apply a bit of trigonometry to get your formulas, and it will be a much more satisfying experience for you than just listening to me. Let's see. So hopefully this is after your attempt at proving this. If y is equal to tangent inverse of x, then x is equal to tangent of y. I differentiate with respect to, so I say differentiate with respect to x. Derivative of x is just 1. Derivative of tangent is secant square of whatever argument you had here times y prime. Now we get y prime is equal to 1 over secant square of y. Okay, we have the answer. I hope this much of it agrees with what you had. Next step of it, again, I encourage you to stop this thing and figure out how to write secant square of y in terms of x. That's going to finalize the formula for you. What was the connection that you had between secant and tangent? Here's one of the Pythagorean formulas we had, was tangent square of y plus 1 is equal to secant square of y. Remember that identity? So secant square of y is equal to 1 plus tangent of y was x. Squaring it is going to give you x squared. So here I'll have secant square of y is equal to 1 plus x squared. So this finalizes our answer here. We did not need to worry about plus or minus cases here. Let's rewrite this thing one more time. Tangent inverse of x prime is equal to 1 over 1 plus x squared. Just to make sure we get used to other style of writing this thing as well. Let's write arctangent prime or a tangent prime x. They are all is equal to 1 over 1 plus x squared. Okay, we have discovered 3 basic formulas. Let's just quickly review what we had. We had the derivative of sine inverse, so 1 over radical 1 minus x squared. We had cosine inverse. It's going to be just negative of this. A good student will be asking himself or herself, why is this particular relationship between these two? Let me leave that to you to wonder about. And tangent inverse of x prime is equal to 1 over 1 plus x squared. Okay, we have 3 more formulas to go for cosecant, secant, and cotangent, which are related to these things, but somewhat messier, especially for secant and cosecant. Cotangent is not all that bad. Before we get there, maybe just do some simple exercises. Suppose I have y is equal to, so here we're going to do some examples. Sine inverse of, say, 2x plus 3. What is y prime? So what are we doing here? We are combining all these things that we just discovered with the chain rule to see what happens. So instead of x, I have 2x plus 3. So I have to do that substitution here as well. Whatever goes here also shows up in this location. I have 2 components. One is this substitution, so which is 1 minus 2x plus 3 squared. The other one is that we have to multiply with the derivative of the substitution here, 2x plus 3. So I have to multiply with 2x plus 3 prime. The derivative of that is just 2. Now this expression could be opened up and create a rather big mess there, but let's just write it because you are going to see similar expressions in calculus 2 especially, so it's a good experience to see it right now. Minus 2x squared is going to be this is minus 4x squared, and 2 times 3 doubled, that's going to be minus 12x, and then minus 9, and 1 is going to make it minus 8, of course. presence of all these negatives shouldn't make you think that under radical necessarily always negative. It all depends on what x is, and of course you have to be careful about what value you choose for x. Same issue was present here. X here had to be less than 1. Whatever you substituted with has to stay in less than 1 in absolute value, that is 2x plus 3, which is substituting this x here, shouldn't be more than 1 or less than minus 1. So if you are worried about the domain of this expression, that 2x plus 3 shouldn't reach 1, it shouldn't go below minus 1 either. So if you want to simplify that, say 2x is less than, here is minus 2, and here is minus 4. You divide by 2, x is between minus 1 and minus 2. The x's that you can use here are between these two numbers, and then you are guaranteed for your radical to make sense and not to be an imaginary number. Okay, that was an example here. If you had made any substitution in any of these cases, you had to do the same thing. Let's go do another example. Suppose I have y is equal to tangent inverse of x squared. What is y prime? Derivative of tangent inverse was 1 over 1 plus square of the input. So I go ahead and write that 1 over 1 plus, instead of x I have x squared, so I have to square that, times the derivative of the substitution by the chain rule. I'll have x squared prime multiply everything else that I have. So that's going to become 2x over 1 plus x to the power of 4. Okay, I hope you go ahead and do more exercises of this type. Let's go quickly take a look at the other 3 trig functions. Let's do the easy one first. Let's take y is equal to cotangent inverse of x. Excuse me. So this means what we want to do, we want to find out what is y prime. The formula tells me that x is equal to cotangent of y. So the derivative of this is going to give you 1 is equal to cosecant square of y times y prime. So y prime is going to be 1 over, excuse me, I had a missing minus here. Derivative of cotangent is minus cosecant square. So minus 1 over cosecant square of y. You remember that identity that says 1 plus cosecant square of y is equal to sorry, I have to make a correction here. 1 plus cotangent square of an angle is equal to cosecant square of that angle. So cosecant square of y is equal to 1 plus cotangent of y was equal to x. So I just put x squared here, and I'll be done with y prime is equal to minus 1 over 1 plus x squared. So what we have here is that cotangent inverse of x prime is equal to minus 1 over 1 plus x squared. Next, we want to take a look at perhaps a secant. So suppose I have y is equal to secant inverse of x, and the question is, what is y prime? Okay, we want to find the derivative of secant inverse. One complication here is that actually different textbooks and authors have slightly different definition for secant inverse. But aside from that, everything else is straightforward. We are going to pick the definition that will give us more of a clear-cut answer. Let's go ahead and see how it happens. If you have y is equal to secant inverse of x, then that means, just as before, this secant of y will be equal to x. I differentiate this. Derivative of x is just 1. In derivative of secant, of course, you remember that is secant tangent. Is that right? Derivative of secant is secant tangent. Now I am applying it to value y, and by the chain rule I have to apply y prime as well. So we are already done with half of this. The y prime is equal to 1 over secant of y times tangent of y. So we found the derivative using the implicit differentiation. Next, I want to write y prime using x instead of y. A secant of y that can easily be replaced by x. Question is, how about replacing tangent of y? How can I replace that? So we go ahead and remind ourselves same basic trig identities that we have seen. These are just Pythagorean identities. What's the connection between tangent and secant? You remember that tangent square of an angle plus 1 is same as secant square of that angle. So if I want to find tangent, I might as well use this formula. This is equal to secant square of y minus 1. If I want to take square root, I'll have the choice of plus or minus square root of secant square of y minus 1. Now tangent of y that we want to replace here, instead of secant I will put x, so I'll have plus or minus radical x squared minus 1. Okay, now comes the critical issue. Which one of these two signs should we choose? Depending on what definition you pick for tangent, for secant inverse, the answer will be different. Here, a definition we are going to use, which is the following. Secant inverse is an angle. Secant inverse of x is an angle in quadrant 1 or 3. That's the choice we make. Let's see what's the output of this choice. If that's the case, so y is in quadrant 1 or 3. Well, what's the tangent of an angle in quadrant 1 or 3? It's going to be positive. And by that choice, this positive sign will be picked. And if that's the case, here on the right hand side, I'm going to have the following. Instead of secant of y, I'm just going to write x, and instead of tangent, I'm going to write this one, radical x squared minus 1, and then I'll be all done. So here is the formula secant inverse of x, differentiated, gives you 1 over x times radical x squared minus 1. Let's just box that. So that was our achievement for the day, the derivative of secant inverse of x. Now, what is all this discussion here? This is really icing on the cake. Here is a higher level discussion as to what's going on here and what's all the debate about. For those of you who might be interested, you remember cosine inverse was an angle in quadrant 1 and 2. So since secant is reciprocal of that, you might expect same kind of a treatment here. If you do like that, then you have to live with the plus minus sign, and eventually your answer here will have an absolute value on it, on the x. That's going to make the formula a little bit messier perhaps. So there's a price either way. Either you live with the absolute value here, or you live with a rather peculiar definition for secant inverse here, one of the two. Let me leave it at that and move on to the final formula for this section. Our next question is, suppose y is equal to cosecant inverse of x. Question is, what is y prime? Let's do that for the sake of completeness as well. So x is equal to cosecant of y. The derivative of this is going to be 1 is equal to, derivative of cosecant is cosecant cotangent minus, so I'll write y and y prime. So y prime is going to be minus 1 over cosecant of y, cotangent of y, just as before. Cosecant is just going to be replaced by x, and the issue is, what would you replace cotangent with? And for that we need to go through the same identity one more round. We have the following formula, that 1 plus cotangent square of y is equal to cosecant square of y. Therefore cotangent of y is equal to plus or minus square root of cosecant square of y minus 1. So cotangent of y that I want to replace here is either plus or minus square root of cosecant is just x, and we are facing the same question as before. Should I choose plus or minus? And similar debate exists here as well, and let me go ahead and explain it. So here y being secant inverse of x, we are going to define the angle y to be in quadrant 1 or 3 again. So excuse me, here y is in quadrant 1 or 3. So cotangent is positive. That makes this choice for us. If we make the choice for the angle y to be in quadrant 3, that is decided for us. And then our answer is going to become minus 1 over cosecant of y is just x. Cotangent of y is going to be radical x squared minus 1. So the offset of all of this thing became cosecant inverse of x prime is equal to minus 1 over x radical x squared minus 1. Okay, so perhaps that's enough of these functions. We are going to go ahead and talk about a very interesting topic that comes up in application in physics and engineering, and that's a topic of orthogonal family of functions. First issue is what is meant by angle between two curves? We know about angles between two rays. Here's one ray, straight line, another straight line, and here's the angle. But what if I have two curves intersecting each other? What's the angle between them? How do you think we should define this concept? Well, it's rather easy. If the two curves have tangent lines, we go ahead and draw their tangent lines. Here's a tangent line to the other one, and the angle between the two curves is going to be the angle between those two tangent lines. There are other ways of defining the same thing, but this is going to do for us. So if two curves intersecting each other define an angle between each other, we can talk about two curves being perpendicular. So next issue is perpendicular curves. Simply means that you have one curve and the other one, and at the point of intersection they make a 90-degree angle between themselves. So here is one tangent line, here is the tangent line to the other one, and if this is 90 degrees or pi over 2 radians, then we call the two curves perpendicular. Well, mathematicians are fond of making some new names, and here instead of perpendicular, which you know from geometry, we use the word orthogonal. Orthogonal curves, they are the ones that have angle of 90 degrees between each other. Now something interesting happens in many physical phenomena, which is you get a whole group of curves and another group of curves with the property that each of the first group is perpendicular to each of the second one. The simplest such picture you see is a group of concentric circles like this, and the curves, the other family of curves will be just straight lines coming from the common center, and you see that they are all perpendicular to each other. So these circles, the black circles and the blue lines, are perpendicular to each other. More interesting pictures you might see, for example, let me draw a coordinate system, and one set of circles, these blue ones, and another set of circles, and so on. Well, if I make all these blue ones with their centers on the y-axis and all of them passing through the origin, and all these pink ones with their centers on the x-axis and passing through the origin as well, then these two groups are going to be perpendicular to each other. Each of the first and second are going to be perpendicular to each other, meaning that I'll be assured that this angle here is 90 degrees. This one here is 90 degrees. This one here is 90 degrees, and so on. They are always perpendicular to each other. Such pairs of families of curves are referred to as orthogonal trajectories in your text. Sometimes just referred to as orthogonal families of functions. Trajectory implies something is moving, but in many physical applications, in fact, nothing is really moving. So here is an example of it. So example problem we are going to consider is this is a problem. Show that the two families one of them being defined by y is equal to something times x cubed, and the other one defined as y squared plus 3y squared plus x squared is equal to b for some number b are orthogonal. Well, we go ahead and find the derivative or the slope on either of these two curves. This one tells me that y prime is equal to 3ax squared. This one, what does that tell me about y prime? This is a little bit unusual to differentiate, but just by implicit differentiation will be straightforward. Derivative of this one is 6y prime. Derivative of the other one is just 2x, and b is just some constant. Derivative of that will be 0. From here I find out that y prime is equal to, simplifying by a factor of 2, I get minus x divided by 3y. Is that right? Can I write this in a style like this? That will make my life a lot easier. Well, if I multiply and divide this thing by x, I go back up here, multiply by an x and divide by x. What's the benefit of that? Well, x cubed times a is just y, so I can write this as 3y. Denominator is x. Now look at these two slopes. What is peculiar about them? Let me call this slope number 1 for the first family, and here's slope number 2 for the second family. They are, of course, you see, they are negative reciprocals of each other. So if I take y prime of the first family times y prime, excuse me, making too many mistakes today, y prime of the second family, what do I get? Product of these two is minus 1. What does it mean if the product of slopes is minus 1? The product of slopes minus 1, it implies that the two curves are perpendicular. The first and second family of curves are perpendicular. And that just finalizes our proof. We are essentially all done. It would be a good idea for you to go graph some of these things on a page and look at them and see how they look like. You have plenty of software available to you to make the job easier for you. Here, let me give you a hint as to what to expect. Y equal to ax cubed. These are just some basic cubic functions. So your typical one, y equal to x cubed, is going to look kind of like this. If you change a to some other number like 2 or 3 or something, you will get perhaps, let me just use a dotted line. So as you change the a, you get slight variation on what this curve is going to look like. The second one, I hope you remember from college algebra what curve this one is. This is an ellipse. We draw it in a different color, say The second family is going to look like this. And the claim that is made in this problem is that these, when they meet each other at 90 degrees. These angles are 90 degrees. The way we proved it was finding the slope to the first one. So this was the slope of the first function, these pink ones, and the second one is the slope at some point on these ellipses. So that was the slope on these curves. At some point of intersection where x and y are the same, we see the slopes are negative reciprocal, therefore the two curves had to be perpendicular to each other at the point of intersection. Okay, you go ahead and do the problems of this section. We covered over quite the territory. Some of these formulas are rather hard to memorize, but you have to try. Good luck and God bless.